Hello, welcome to Maths with EJD. In this video, we're talking about the ratio test for convergence. Under convergence, test for convergence, right? Ratio test. We had considered previously three other tests, the first being the nth term test for divergence. Then we saw the integral test. We also saw the comparison test. Now we are off to check out ratio test, which I think is about my best of all the tests because I like the style. You just go to the next step of a particular sequence you're given and try find the limit and you get your result. So let's see how this works. So starting with the concept of this now, okay, starting with the concept of the ratio test, it just tells us let L be the limit as n goes to infinity for an plus 1 divided by an, okay? If that is the case, right, what do you do? First, if that L, if the limit you get is actually less than 1, the series, the series converges absolutely. The series converges absolutely. As far as you can get the limit to be less than 1, the series converges without any doubt. Okay? If L is greater than 1, or actually L is equal to infinity, L is equal to infinity, then clearly the series diverges. The series diverges. Then lastly, if L if L is equal to 1, then the test is inconclusive. The test is inconclusive. Now you see why I really like this test. All the conditions are clearly spelled out. So that's why I really love it. So let's go for the first example. So let's go for the first example. That's example one. Okay. Example one. Example one. So let's test the series and summation from n equals 1 to infinity of 1 over n factorial. That's what we want to test now. I think we did something like this when I was talking about power series. Okay, so let's test this. So the first thing we want to do is to compute. So yeah, this is what we want to test, right? So then we need to compute. We need to compute L, which is limit as n goes to infinity for an plus 1 all over an. Clearly here, this this simply implies that this expression tells us that an is equal to 1 over n factorial. That's what an is in this case. So an plus 1 is just us stretching it, taking it to the next level, if I may say that. So that means we have L to be equal to limit as n approaches infinity, and then 1 over n factorial, of course, 1 over n factorial simply tells us that an plus 1 is simply 1 over n plus 1 factorial, right? So this means that we have this now. This will be 1 over n plus 1 factorial divided by 1 over n factorial, like this. If that is the case, we can try to resolve that, and we have limits as n goes to infinity for 1 over n plus 1 factorial divided by 1 over n factorial, like this. So that means L is limit as n goes to infinity for 1 over n plus 1 factorial times n factorial, like this, so that L now is equal to limit as n goes to infinity for n factorial over n plus 1 factorial, right? So that we're still in line. We have to keep resolving that. So L is now limit as n goes to infinity for n factorial. N plus 1 factorial is simply the same thing as n plus 1 times n factorial, because we know the whole idea of factorial is that when you have n factorial, it's the same thing as n times n minus 1 times n minus 2 until you go all the way down to 1. Okay, that's the idea of factorial. So that means n factorial can cancel n factorial. So we have L to be limit as n goes to infinity for 1 over n plus 1. So at this juncture, you can actually, so the absolute value of 1 over n plus 1 is simply what it is because there's no other things to worry about. So limits as n goes to infinity for 1 over n plus 1. One of the first things you can do is to substitute the infinity directly. But if you do that, it's going to make the results, okay, I think we're just going to get 0, yeah? Because even if you divide by n, you have 1 over n, it's 0 at the top. So we can just do that straight up and we are good to go. So this is 1 over infinity plus 1, which is 1 over infinity, and that is 0. And when we get 0, what does that mean? The condition is if L is less than 1, the series converges absolutely. So L is equal to 0. So we say therefore L is equal to 0, and that is definitely less than 1. Okay, because it's less than 1, what do we conclude? We just say uh since say since L is less than 1, the series summation from n equals 1 to infinity of 1 over n factorial converges absolutely without any doubt. It converges. Okay, so that's how that goes. Okay, now let's go ahead and do another one. Let's take example 2. So for example 2, now we want to test the series n equals 1 to infinity n factorial. So here, what do we have here? We have that an is equal to n factorial. That implies that an plus 1 is equal to n plus 1 factorial. Okay, so that tells us that L, that simply means that L is equal to the limit as n goes to infinity for the absolute value of an plus 1 all over an. Okay, that then means that L is equal to limit as n goes to infinity for an plus 1 is n plus 1 factorial up there all over n factorial. So L now is equal to limit as n goes to infinity. And then we can break that down. So we know n plus 1 factorial is the same thing as n plus 1 times n factorial. Okay, n plus 1 times n factorial all over n factorial. So this cancels out. So we have L to be limit as n goes to infinity for the absolute value of n plus 1. Of course, if you have the absolute value of n plus 1, it is what it is, like they say. And that means we have L to be limit as n goes to infinity. And that's simply n plus 1. If you substitute the infinity directly, that means L is equal to infinity plus 1, and that is simply infinity. Okay. And what is the condition? It was clearly stated from the outset that if L is greater than 1 or L is equal to infinity, the series diverges. Okay. So we can conclude that now that since L is equal to infinity, then the series we started out with, the series summation from n equals 1 to infinity of n factorial diverges. So it clearly diverges. Okay. So that's yeah, with that we come to the end of the ratio test, which I love so much because I like the fact that everything is clearly spelled out. Of course, it's not like other things are not clearly spelled out in other cases, but I just like the approach in this case. All right, so you can try more example. Let me see if I can get more examples for your practice. Let me try to do that. More ratio tests, examples. Okay. So you can take this as practice questions. So let me say practice questions. Okay. Practice questions. So test. So like we've been saying, test the series n equals 1 to infinity for n factorial over 2 raised power n. I want to test that. That is 1. Number 2, we also want to test, okay, we've done 1 over n factorial. So can you also test the series? Can you also try to test this series? N equals 1 to infinity, then 3 raised power n over n factorial. You want to try that out. Then can you check? Okay, this is number 2 now, not 3. Number 2 is number 2. Then number 3, can you also try this? Summation n equals 1 to infinity of n raised power n all over n factorial. You want to try that too. Then I have a fourth one. So many. I have a fourth one. Summation. Okay, I guess I want to give that a bit of space. So 1, 2, 3. The number 4 is summation for n equals 1 to infinity of 5 raised power n all over n raised power 3. So you just want to check that out. Yeah, so we have all this. So try your hands on them and see how well you get them. Okay. So I think that brings us to the end of the ratio tests, but of course not to the end of the sequences and series playlist for sure, because in the next video, I'll be talking about some special series that actually always diverge. So we're going to talk about divergence of certain series, divergence of certain series. So this is your practice question again. Don't forget. All right. So if you have not subscribed to this channel, be sure to do that right away and hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know how helpful these videos are to you, and let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. Then like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.